Okay, I have to start today's deep dive with a story. It's an absolute classic in the world of computer science. It might be a little apocryphal, but it is just too good not to share.
I think I know exactly where you're going with this.
Oh yeah,
Is this the famous Cold War translation experiment?
it is the Bible code disaster, yes.
Yeah.
So picture the scene. It's the 1960s. Early engineers are testing one of the very first machine translation systems. They feed it a line from the Bible. The spirit is willing, but the flesh is weak.
A poetic, very metaphorical sentence, so a high difficulty level for a calculator.
Exactly. So they ask the computer to translate it into Russian, and then to double-check the accuracy, they feed that Russian text back into English.
And let's just say the result wasn't exactly divine scripture.
Not even close. What came out was, the vodka is strong, but the meat is rotten.
It kills me every time. But, it's a funny story, but it's also a perfect illustration of why this is so hard.
How's...
The machine did exactly what it was told. It looked up spirit. Spirit is alcohol, okay? Alcohol is vodka. It looked up flesh. Flesh is meat. I mean, it was technically correct, but it completely missed the soul of the sentence.
And that distinction between being technically correct and actually understanding, that's what we're unpacking today. We've got a stack of research here on what they call applied linguistic systems.
Which, I know, that sounds incredibly dry. It sounds like a dusty university lecture.
Right. But it's actually the engine behind the tools you use every single hour of the day.
Spell checkers, search engines, Google Translate, all of it.
The mission here is to explore how computers try to process our language, why they fail so often and so funnily, and really why teaching a computer to read is one of the hardest problems in science.
It's the difference between doing math and writing poetry.
Yeah.
And honestly, looking at these sources, even the easy stuff is a nightmare.
Let's start right there. The basics. You'd think the easiest thing a computer can do is just, put text on a page.
Just print the letters, sure.
But looking at these notes on hyphenation, I'm realizing I've totally taken this for granted.
Oh, absolutely. Hyphenation is a minefield.
Mm.
And it really matters because if a computer gets it wrong, it actually breaks your brain's ability to read smoothly.
Because we don't read letter by letter, right? We scan chunks of words.
Exactly. So when a computer runs out of room on a line, it can't just count characters and chop the word in half. If you do that, you get gibberish. You have to break it by syllables.
Which requires rules.
And complex rules. The source material uses some great Spanish examples. Take the word recibo, I receive. You can split that as recibo. That works.
Okay, that sounds natural.
But you absolutely cannot split it as recibo.
Because that leaves a lonely little vowel dangling at the end.
Right. It violates the phonetic rules of the language.
Right.
But here is where it gets tricky, and this is the key takeaway for you listening. Computers don't naturally hear syllables. You have to program that logic in.
Okay, so you just teach the computer. Consonant, vowel, consonant, problem solved.
If only. To do it really well, the system needs to know the morphemic structure. Basically, the history of the word.
The history.
Yeah. The notes mention the word soberbano. A simple syllable counter might chop it up based on sound alone. But the correct split has to see that sub is a prefix. It's its own unit, so it has to be soberano.
So the computer has to be an etymologist just to know where to put a dash. That's wildly complicated.
Precisely.
Yeah.
And then you throw in proper names. The source mentions the difference between a Spanish name like Pellicer and a foreign name like Schiller.
Okay.
In Pellicer, that double L is a single sound in Spanish, so you can't split it. But a simple program applying Spanish rules to the name Schiller might mess it up. You basically need a massive dictionary of every name on Earth.
So even just wrapping text requires a dictionary and a degree in linguistics. That makes me feel a little more sympathetic to my word processor. But let's talk about the feature that saves my life daily. Spell check.
The safety net.
But the sources point out that spell check has some massive blind spots. And reading this, I realized I've been trusting it way too much.
It does. I mean, first, we have to distinguish between a typo and a spelling error. A typo is just a slip of the finger. A spelling error is when you genuinely don't know the word.
Right. If I type a string of letters that doesn't exist, like Gordy, the computer puts that red squiggly line under it. Easy. It's just checking a list.
That is the easy part. The real danger, the translation trap of spell checking, if you will, is what they call the real word problem.
This is when I make a mistake, but the mistake I make creates a word that actually exists.
Exactly. The source gives a hilarious Spanish example. Cazar with a Z means to hunt.
Okay.
Cesar with an S means to marry. They sound very similar. So if you type, I want to hunt my girlfriend instead of marry, the spell checker looks at it and says,
Hunt. That's a real word. Looks good to me. And you end up with a very confused girlfriend.
Or a restraining order. The computer doesn't know you love her, it just knows hunt is in the dictionary. And then there's morphology, the shape of words.
Right, like grammar.
The sources note that standard checkers are often bad at catching irregular grammar forms. Like if you typed teached instead of taught, a basic spell checker might just flag teached as misspelled instead of realizing the verb tense is just wrong.
So that leads us directly into the bigger boss battle, grammar checking. If spell check is just looking at words in isolation, grammar checking must be, just exponentially harder.
It is so much harder. Think of the computer as a traffic cop. Spell check is just checking if a car has a valid license plate.
Okay.
Grammar checking is watching to see if that car runs a red light, cuts someone off, or is driving the wrong lane. It has to monitor the flow.
And the sources really emphasize that the biggest challenge here is agreement.
Right. In many languages, like the Spanish examples in the text, words have to change shape to match each other. Nouns and adjectives have to match in gender and number.
You can't have a feminine table, la mesa, and describe it with a masculine adjective, largo.
To a human ear, las mesas son largos. It sounds like nails on a chalkboard. It's just wrong.
But to a computer.
It's just data. And here's a key insight from the research. The difficulty for the computer is determined by distance.
Distance. You mean how far apart the words are in the sentence?
Exactly. If I say red apple, the words are touching, the computer sees them, checks the rules, easy. But what if I say the wooden tables, which I bought yesterday at the vintage store, are very long?
Okay, there are like 10 words between tables and long.
Exactly. To catch that error, the computer has to hold tables in its short-term memory, scan through all this irrelevant stuff, and then bam, connect it to long at the very end.
It has to keep the thread.
And computers often drop that thread. This is why the sources mention that scathing review of an old grammar checker called Grammatic. They said, nobody needs a program that's wrong in more cases than it's right.
Ouch. That is brutal. But I feel that. When the blue squiggly line tells me to change something and I know I'm right, I don't think, oh, silly robot. I think, I am turning this feature off.
And that's the noise problem. If the false alarms are too high, you just stop trusting the tool entirely. And sometimes it's not even an error, it's just style.
Oh, right, style checking. This feels like the computer trying to be a literary critic.
It's often just math masquerading as taste. It might flag a sentence as too long just because it has more than 20 words. Or in Spanish, it might count how many times you use the word day of. If you use it 10 times, it says bad style.
It's prescriptive, like a grumpy school teacher with a ruler.
It is. It also flags colloquialisms. The text mentions it might flag the word parking in the Spanish text and demand you use estacionamiento. It's trying to enforce a formal standard.
So, to make the computer smarter, we need to give it a better map of language. The notes mention these things called ontologies, like WordNet. These sound like more than just dictionaries.
They are so much more. Think of a dictionary as a flat list. An ontology like WordNet is 3D. It maps concepts. It knows that a canary is a type of bird, and a bird is an animal. It groups words into synsets, sets of synonyms.
So it knows car and automobile are basically the same node in this big web.
Right. And it knows opposites and subclasses and parts of a whole. And this is crucial because it lets the computer understand relationships. If you search for vehicle, a system using an ontology knows to show you documents about cars, even if the word vehicle never appears.
That is a perfect segue into the next big topic, information retrieval, or, as we all know it, Googling things.
Right. Information retrieval, or IRS, is the science of finding a needle in a haystack.
Yay.
But not just any needle, the specific needle you actually want.
And the sources talk about this constant tug of war between two ideas, recall and precision. Can you break that down for us?
Sure. Imagine you're fishing. Recall is throwing a giant net.
Okay, so you catch everything.
You catch every single fish in the lake. You definitely got the one you wanted, but you also got old boots, tires, and 1,000 fish you didn't want. You have high recall, but very low precision.
And precision is like spearfishing.
Exactly. You aim for one specific fish, you get it. No boots, no tires. But you might have missed 50 other fish that were also relevant. Search engines are constantly trying to balance this.
Like, if I search for Java, does it show me the island, the coffee, or the programming language?
And if you want the coffee and you get the programming language, that's noise. So to reduce noise, systems use stop words. These are frequent, meaningless words like the, and, that the computer usually ignores.
It's interesting how the sources discuss summarization here, too, because once you find the documents, you need to know what they're actually about.
This is where we see a fascinating shift in technology.
Mm.
There are two main approaches mentioned. One is the old-school dictionary-based method, like a system called Classitex.
And it basically just counts words.
Pretty much. It neutralizes words. So regimes becomes regime, and then it checks a hierarchy. If it sees sentence, verb, and noun a lot, it says, all these words are in my linguistics bucket. This text is about linguistics.
So it's a democracy. The topic with the most votes wins.
Yes, but there's a huge flaw. The source points out that Classitex ignores pronouns. In Spanish, the subject is often implicit. So you might have a paragraph about a politician, but after the first sentence, the text just uses he.
So the system misses all those references because he isn't a topic in the dictionary. That's a huge blind spot.
It is. So the alternative is neural networks, like the text analyst system. This doesn't use a dictionary at all. It looks for relationships.
How does it know what words mean without a dictionary?
Think of it like high school. If you want to know who fits in which social group, you don't look at their ID cards. You look at who hangs out with whom.
Ah, I see.
Text Analyst notices that software and Microsoft appear near each other a lot. It builds a web of connections based purely on proximity. It's less about what does this word mean and more about who does this word hang out with.
I love that. Who does this word hang out with? Which brings us back to the most notoriously difficult area, machine translation. We started with the vodka disaster, but surely we've moved past that.
We have, but the core problems, the ambiguity, they remain. The source brings up a commercial system, Power Translator, that took the header plans from a document and translated it into Spanish as planifica.
Boom.
Planifica is the imperative verb. It's a command. You plan this. But the header plans is a noun. It should have been planes.
But the computer saw plans, which can be a verb or a noun in English, and it just guessed wrong.
Ambiguity is the enemy. The Spanish word gato is the ultimate example. It can mean cat, a card shack, a trigger, or a sneak thief. Without deep context, the computer is just rolling dice.
The sources had a great example of this that really broke my brain. Jose gave Maria a book. It is interesting.
A classic dilemma. In English, we have it. But if you translate that into a gendered language like Spanish, you have a problem. Es interesante doesn't specify the subject.
Right.
So if you're translating that back into English, does it mean the book is interesting, Maria is interesting, she or Jose is interesting? And the computer has to pick one.
It has to guess. And often it guesses based on statistics, not on an actual understanding of the story.
Then there's the computer shop problem. This one really highlights the gap between logic and world knowledge.
Oh, the implicit number problem. Computer shop. In English, we use computer as an adjective. But in Spanish, is it a shop of one computer, computadora, or a shop of many computers, computadoras?
Obviously, it sells many computers. A shop with one computer is just a guy with a laptop.
Obviously to you. But grammatically, computer shop is singular. A machine might translate it as tienda de computadora, a shop that sells one solitary computer. It lacks the common sense. And that common sense is world knowledge. This leads perfectly into interfaces talking to databases. The source mentions the elliptical problem.
This is how humans actually speak. We don't use full sentences.
Yeah.
If I ask a database, are there wide printers? And the system says no, my next question is just.
And narrow.
And narrow. You don't say, are there narrow printers in the store? The computer has to understand that. And narrow.
Yeah.
Inherits all the context from the previous question. It has to model your intent.
We take that for granted. We fill in the blanks automatically.
You do, and we do it with vision, too.
Yeah.
The section on OCR optical character recognition was really interesting. We think of it as just seeing letters, but it's actually linguistic guessing.
Because shapes are messy, right? Like a lowercase L and the number 1.
Exactly. Or R and N squished together look like an M. The computer sees a shape that looks like Danios, that's not a Spanish word, so it checks its dictionary.
And it finds alternatives.
It sees Darnos, give us, and Damos, we give. It has to use the context of the whole sentence to decide if that blob of ink was an RN or an M. It's not just seeing, it's reading.
So bringing this all together, we have spell checkers that misteached. We have translators that think plans is a command. The ultimate goal, the sources say, is natural language understanding, NLU.
This is the holy grail. NLU is the difference between processing symbols, just moving math around, and actually reasoning. The Turing test is the benchmark. Can a computer hold a conversation so well that you can't tell it's a machine?
And based on everything we've read today, we are not there yet.
We are not. We've mastered a lot of the mechanics, we can do the math, we can fix recibo and find synonyms for car, but the soul of language, knowing that a computer shop sells more than one computer, or that the spirit is willing, isn't about vodka. That requires understanding the world, not just the dictionary.
It's like the computer is a tourist with a really good phrase book, but it doesn't actually know the culture.
That's a perfect analogy. It knows the words, but not the music.
So for you listening, the next time your phone autocorrects something completely wrongly or Google Translate gives you nonsense, don't get mad. Just remember, it's trying to do math on poetry.
And it's doing a surprisingly good job, considering it doesn't have a body or a life or a brain.
And here's a thought to leave you with. If we eventually want computers to truly understand language, to get the jokes, the metaphors, the implications, does that mean the computer has to experience the human world first?
That is the big question. Can you understand pain or hunger or love words we use constantly if you are just code in a box? Can you understand sweet if you've never tasted sugar?
Or is language just a complex code that can be cracked without ever needing a physical body? It's a fascinating problem, and we're living right in the middle of it. Thanks for diving in with us.
A pleasure as always.
We'll see you next time.